Welcome to CST 351 Lesson 4, Search Techniques 2. We will cover types of AI search strategies and evaluation of search performance. To recap from last week, we covered AI problem solving by search. We covered search as problem solving. We talked about the 6 components of a search problem. We talked about state space and combinatorial explosion and the need for efficient exploration strategies. And it's very important to note again that the 6 components of a search problem entails the initial state, then the action, that is the set of the legal moves, the transition model, that is a state after an action is executed, the goal state, the path cost, and then the state space, which is a graph of all reachable states from initial states connected by actions. Now, for this class, we will dive deeper into uninformed and informed search strategies. We'll compare BFS, DFS, greedy, and A-star algorithms. We'll evaluate these algorithms using formal criteria and then justify algorithm choice for a given problem. Now, the search strategies can be grouped into 2. We have the uninformed blind search, which is BFS and DFS, and the informed search, which is also referred to as heuristic search, which is entails greedy algorithm and A-star algorithm. There are several algorithms, but we are just focusing on these 4 algorithms. For uninformed search algorithm, which is a blind search algorithm, we have BFS and DFS. These algorithms do not use any domain-specific knowledge about the problem being solved. They rely on the information given in the problem definition, and so they lack heuristic function to guide the search towards the goal. They explore the search space systematically without additional guidance and provide fundamental strategies for searching when no extra knowledge is available. Useful in various AI problem-solving scenarios, including pathfinding, puzzle solving, state space search, amongst others. So applications of uninformed search algorithms include pathfinding, puzzle solving, game AI, robot navigation, and web crawling. So let's look at the breadth-first search algorithm. It expands the shallowest nodes first. So it's complete, it's optimal. We talked about it in last class, but let's see how it works. So this is the BFS state space graph. So what it does is, let me get pointer options. So what it does is that, suppose the AI is starting from A and intends to get to G, which is the goal. For breadth first search, it explores all nodes layer by layer. So it goes to A first, it starts from A, then branches to B and C, then goes to B, branches to D and E, then comes back to F and G. It cannot go back to C because it has already visited C before. Okay, so the path will be A, B, C, D, E, F, G. So it's layer by layer. So it goes A, that's the first layer, which is the start. B, C, that's the second layer. Then D, E, F, G, till it gets to the goal. And here is the expansion order: A, B, C, D, E, F, G. It's very, very straightforward. We've talked about the time and space complexities in the previous class. Please refer to the previous video. The second is the depth first search. It expands to the deepest nodes first. And so here are the properties. It's not optimal, not complete, and just refer to the previous note to see the advantages and disadvantages. So for depth first search, it goes to A and goes to B and goes to D. So it goes to the depths, down, 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 till it gets to the end, to the leaf node, then it backtracks. So for here, it goes to A, B, D, right? Then E, then C. Very straightforward. A, B, D. Then it backtracks, go to E, then it goes to C. Okay, so the next is let's look at why uninformed search fails. And the main challenge, we talked about it in last class as well, is combinatorial explosion. and so on and so forth. So let's proceed because of time. Now let's look at informed search, which is also referred to as heuristic search. Now, informed search algorithm in AI uses additional knowledge known as heuristics to guide the search process. They prioritize paths that are more likely to lead to the goal by estimating how close a step is to the goal. These algorithms find solutions faster and more efficiently than uninformed or blind search methods. So they are commonly applied in AI for tasks such as path finding and solving puzzles. And these algorithms are quite useful for navigating large and complex search spaces. So here are some of the applications of informed search algorithms: pathfinding in navigation systems, game playing, robotics, problem solving in AI, and so on and so forth. So let's look at two common examples of informed search strategy, which is greedy best first search. So greedy search selects the node with the lowest heuristic value, estimating closeness to the goal. So the evaluation function f of n for the greedy equals h of n, where h of n is the estimated cost from node to the from the node, the given node to the goal. G of n, which is the path cost so far, is not considered because generally we have both h of n and g of n, right? So g of n is the cost so far, okay, the cost acquired so far, while h of n is the estimated cost from the node to the goal. So for example, in this greedy search algorithm, h equals 6. H is the estimated distance to the goal, okay? So from A to G, the estimated cost is 6. From B to G, the estimated cost is 4. From C to G, the estimated cost is 2. From D to G, the estimated cost is 3. So to traverse this, the algorithm will go to A first, then it will look at the two branches B and C. Which one is shorter? Which has a shorter distance to the goal is 2. 2 is smaller than 4. So it will the next node will be C. So after we have A, we'll have C, right? Now C is connected to only the goal, so it's going to be A, C, G. Very straightforward. And you can see here the H value at the goal is always 0 because it's 0 distance to itself, which is quite obvious. So for a search algorithm, a search is an informed search algorithm that combines the actual cost so far to the estimated cost to the goal. So we already know what h of n is, which is the estimated cost to the goal. Now g of n is the cost covered so far from the start. Okay, so let's look at this. This is the start, right? So the cost covered from the start is going to be 0 because it has not moved anywhere. That's the start. Now that's why g of o is 0 for x. Now h of x, h is h of n, I mean, is 6. That means the distance between s to the goal is 6. So h is 6. The distance between s to the goal is 6. So the sum of g of n and h of n, which is 0 plus 6, equals f of n, which is 6. Okay, so we are starting from s. We are looking at the value of f, mind you, which is the sum of the two. Okay, the estimated cost to the goal and the distance covered so far. So A has covered a distance from the start, which is 2 already. It has covered 2 already. And we are talking about cost. So also the distance between A to the goal, G, is 4. Okay, it is 4. So, and the sum is 6. Also for B, the sum is 6. Okay, so it will try A, right? 6 is 6. A is connected to C, which is also 6, right? Before the goal, right? So it will also try B and try D, but D is not even connected to the goal. So there's no need to even go there. There's no connection. And as you can see, it's even 8. So it's not an option. So it goes through A to C and to G, which is connected to the goal. And so the order is S, A, C, G, which is very, very obvious. So now let's look at the algorithms. For the 4 algorithms, think of them as a to-do list manager. They all follow the same logic, but they differ only in how they pick the next item from the list. So the general blueprint is, number one, start with a list of places to visit, which is the to-do list. Then number two, pick a place from the list, right? If it's the goal, stop. Else, add its neighbors to the list and then repeat. Let's look at the algorithm for the breadth first search. So this code implements a breadth first search um, algorithm to determine whether a target node goal can be reached from a starting node, which is start in a graph. So the target node is goal and the starting node is start. So line 1, this line defines a function named BFS that takes 3 parameters. Graph, which is a data structure, typically a dictionary. For those of us who are familiar with Python, where each node maps to a list of its neighboring nodes, right? Then we have the start. This node, this is the node where the search begins. And then the goal, the node we are trying to find. So we have the graph, which is a data structure, typically a dictionary. We have the start, which is the node where the search begins, and the goal, which is the node we are trying to find. Okay, so line 2, to-do list equals start. Now, a list called to-do list is created to keep track of the nodes that still need to be explored. So it is initialized with the start node, meaning that the search begins there. So this is a list that keeps track of all the nodes to be explored. And we have to initialize it because we are starting from the start node. That's why we are initializing it with start, okay? So line 3, visited is a set. It's created to store nodes that have already been explored, okay? So this one stores the nodes that we are visiting, which is initialized with start. But this one is a set that stores the nodes that that are already have been explored. Using a set allows us to fast look up and prevent revisiting the same node multiple times. So while this to-do list takes a value, right? The set takes several values. You know how a set looks like. It takes several values. So get that clear so that we will not visit a node multiple times. Okay, it's very, very important. So line 5 is a loop, right? This loop continues. This loop continues to run as long as there are nodes left to explore in the to-do list, right? If the list becomes empty, it means all reachable nodes have been checked. Then line 6, the first element of the to-do list is removed and stored in current. The first element in the to-do list is removed and stored in current. Removing from the front ensures that the nodes are processed in the order they were added, which is the defining behavior of breadth first search. First in, first out. Now, 7, the algorithm checks whether the current node is the target node. So if the current node being visited is the goal node, which is where we are going to, it stops, it returns found. If the current is not in visited, right, that means you have to visit that node. This condition ensures that the node is processed only if it has not been visited before. So that's where this comes in, right? So if the node where we are in has not been visited before, then go ahead and visit it. So the current node is added, line 11, the current node is added to the visited set to mark it as explored. Then 12, all neighbors of the current node retrieved from the graph current are added to the end of the to-do list. This ensures that neighboring nodes will be explored in future iterations. So, and for the iteration for the loop to continue, it has to return not found. So that is if the while loop finishes without finding the goal, meaning the to-do list is empty, the function returns not found, indicating that the goal node is not reachable from the start node. So, and this explanation is similar for all other algorithms. So you can look at the other algorithms as well. Depth first search, DFS, greedy best first search, and A-star search. So now let's quickly look at an executable code. If you click on this link, the slides will be shared as well. If you click on this link, it will take you to an executable code. Please run that code in Python. So let's try to run this code online. So the code looks like this. The data with sample data, of course, and then the algorithm. So you can run this. Let's try to run it. So I'm running it online because I do not want to install Python on my system. So I'm using Cloud, Programmist Python online compiler. So I've pasted the code here. I hope we are seeing this clearly. So I pasted the code here. Sorry if it's truncated. You have the code on that file. Okay. So I will click run to see the output. Okay. So for BFS, this is the path start, then A, then go. Then for A star path, start, then B, then go. So you can look at the input we have included here. We have the graph, sorry, it's truncated. We have the graph initialized. And what this means is that we are starting from node labeled start. This node is labeled start. And start is connected to, is branching out to A and B, right? A is branching out to B and goal. And B is branching out to goal. Goal is terminal. Okay. I think, okay, so let me try to explain this in the PowerPoint file. Just a second. I will explain that shortly, but let's quickly finish up. So, so the summary is that search strategies defines AI efficiency. Uninformed search is limited. A-star balances optimality and efficiency. Is actually the best. And evaluation criteria guides algorithm choice. Okay. So, and here are the sources. So let's quickly look at the first part of that code, the sample data being shared. So we have the start. I don't know how clear this is now. We have the start, right? Now, the line says start is connected to A and is connected to B. Start is connected to A, is connected to B. Then B, A is connected to B and the goal. So A is connected to B and also connected to the goal. A is connected to B and also connected to the goal. And then B is connected to the goal. Simple diagram and straightforward. Don't know whether this camera is clear, but at least just to give you an idea of how it looks like.